Good morning, evening, or whatever you're doing. Today we're going to talk about Lesson 2.2 notes, and it's over power functions with modeling. We just got through talking about linear functions and quadratic functions, and so the power function is just using powers or exponents in our function. The power function looks like this: f of x equals k times x to the a power, where a cannot equal 0. If a were 0, then we would have just f of x equals k, which is a constant function. Here, k is the constant of variation. And when we read this problem, we say that f of x varies directly as x to the a power. And this varies directly. Whenever I read this part or I have a word problem and it says varies directly, that's where I'm going to put my k. Okay? And k being a constant, that just means basically that if I'm comparing two things, this is the relationship, the constant relationship as they change, the ratio of them. It says power function formulas with positive powers, so where a is greater than 0, are what we call direct variation, and power formulas with negative powers are statements of inverse variation, and we'll look at those two different kinds of functions there. Okay, we have 7 basic power functions, and they are x, which would be x to the first power, x squared, x to the third power, 1 over x, and 1 over x is a power function because it can be written as x to the negative first power. Then we have the square root of x. Again, the square root of x can be written with an exponent by saying x to the 1/2 power. Cube root of x would be x to the 1/3 power. And then 1 over x to the second is very similar to 1 over x. That would be, got a little ahead of myself, that would be x to the negative second power. Okay, we've got a couple of power functions here to look at, and what we want to do is state the power and the constant of variation for each function and graph it and analyze it. So let's just look at the first one. We won't worry about a just yet. If you have a graphing calculator, I would recommend graphing it. I will show you the form that it takes. If we were to rewrite this with an exponent, it's going to say x to the 1/3 power. So in this case, the constant of variation is just the coefficient in front of the variable. So in this case, it would be 1. And the exponent, or the power, is 1/3. And then we want to look at what would the graph of this function look like if we take x to the 1/3 power. It looks a lot like the cube function. We have our coordinate plane, and then the graph of this would look like something like this. Very similar. Again, if you have a graphing calculator, go ahead and graph the cube root of x and take a look at the graph of that. And then we're going to go over just the different parts of the graph, and this is the part where we go to analyze it. When we're talking about the domain, we're talking about all of the x coordinates, and so the domain is going to be negative infinity to infinity. The range are all of your y coordinates, so we go from along the y-axis going up. It's kind of hard to see this one, but it is going from negative to infinity to infinity along the y-axis. It is a continuous function, and for this one it's increasing. Some parts it's increasing rapidly, some parts it's a very gradual increase, but it is increasing from negative infinity to infinity, so there isn't a decrease in that. Symmetry, this one is odd symmetry. Okay, that's where, again, we take that function. If you're looking at a graph and you want to rotate it 180 degrees, and if it looks the same, then you have an odd function. And then boundedness, it's not bounded. I'm going to have to scroll down in order to see the rest of it. Okay, we stopped at the boundedness. Again, we had our function looks like this. It's not bounded. It has no extremes and no asymptotes, horizontal or vertical. The end behavior is what's happening along the x-axis from left to right. So end behavior would be going to the left, and then another end behavior going to the right. And in both instances, when it's going to the left, it's negative infinity, and when it's going to the right, it's positive infinity. Not the real technical way to write that, but I think it makes a lot of sense. Okay, if we look at the next function, we have 1 over x squared. We can rewrite that as x to the negative second. So this time, the constant of variation is still 1 because we have a coefficient of 1 on the x, and then your power, or your exponent, is negative 2. And then we'll look at the different parts of that. We've got domain and range. The domain is from negative infinity to 0, and then 0 to infinity. Again, you should graph that function. Let me just real quick sketch it for you here. But if you graph it, you can have a little bit better idea of what's going on. And so that's the sketch of my graph. A very rough sketch. The range goes from, actually from 0. It doesn't touch 0, so I'm going to use those parentheses, and then to infinity along the y-axis. It is infinite discontinuity. And increasing and decreasing, it's doing both. So it's increasing from negative infinity, and as it's approaching 0, and then it's decreasing from 0 to infinity. The symmetry, this one has even symmetry because it's symmetrical across the y-axis. It is bounded. This one's actually bounded below. But we don't have any extreme values, ones that just kind of stick out there, and because we have to have either a peak or a trough in this, and we don't have either. So there's no extreme values, none. Now, as far as the asymptotes go for this function, we actually have a couple of those. The way this is working. Looks like that and that. And so I'm going to list my vertical asymptotes first. We'll call that the VAs. Vertical asymptote is just a vertical line where it approaches, and it's approaching where x equals 0. And then we also have a horizontal asymptote where y equals 0. And then our end behavior is the same as the function for example 1. As we're approaching the negatives, go to negative infinity and positive infinity. Okay, now we're going to take a look at monomial functions, which can also be power functions or are power functions. And I'm just going to list some examples of that to help you out a little. You could have a constant function, so that would be a monomial function with one term. F of x equals 4x. That would be an example of a monomial function. Yeah, I put a exponent of 3, and then f of x equals 4x squared over 3. Now, even though we have a denominator there, that's fine. The thing that you need to be aware of is that the exponents must be greater than or equal to 0. And then you've got a monomial function. Otherwise, you're going to have the, if you make it a positive, you're going to have your variable in the denominator, and then it's not a monomial function anymore. All right, examples 2 says, tell whether each statement is a monomial, and for those that are, we're going to state the degree and leading coefficient. So for A is not a monomial function, and it's not a monomial function because it has a negative exponent. For B, no, it's not one either because our exponent is the variable as well. And then this one's a yes. We have two variables, but if let's say we know the length is a value, and W becomes the variable in the problem, or vice versa, we can switch it around. So in this case, we say yes, the degree is 1, because the variables have an exponent of 1, and the leading coefficient is also 1. Okay, this next problem says write each statement as a power function equation. Variation and proportional are interchangeable. So when they talk about something that varies directly or is proportional, they're really talking about the same thing here. So part A says the volume V of a cylinder with fixed height is proportional. So that's direct variation to the square of its function. So we say V is means equals, the volume equals. When something is proportional or varies directly, it's going to be K times, and then we're going to take the square of its radius, which is r squared. So there's our function, V equals K times r squared. Okay, and then for part B, we have the current I in an electrical current circuit is inversely proportional to the resistance R with constant of variation V. When we have I is inversely proportional, we're not going to multiply, but we're going to put K on top as a numerator, and it's inversely proportional to the resistance, which is R. Then it comes back and says, well, actually our constant of variation is V. So we're going to replace the K, which represents the constant of variation, with V, and we get I equals V over R.